Greetings, listeners, and welcome to our special 4-part series all about one of nature's most beautiful spectacles, the aurora. Brought to you by Sky at Night magazine and Herta Grutten. Episode 1. How to observe the aurora.
Today I'm talking to expert aurora chaser Tom Kerss, an astronomer, a writer and a podcaster who's had more than a few aurora adventures over the years and who even wrote a book about them called Northern Lights, the Definitive Guide to the Auroras. Tom, thanks very much for coming on the podcast and speaking to me today.
Thanks, Ian. It's a pleasure to be here talking about my favourite subject.
Maybe someone who's never seen the aurora before, how would you describe it? What's the experience like? What does it look like?
That's a tough question, to be honest, Ian, because I think genuinely the aurora's one of the few things in this world that could be considered actually indescribable. I mean, lots of writers have tried. I haven't tried to describe it in my book because I'm not a great writer and I'll always fall short. So the answer is always that you have to see it for yourself to know what that's like. All I can say is that from my perspective, it's like taking something out of a dream and putting it in the sky. It has an unreal quality to it. And it really is like nothing else that you can see in the sky or indeed anywhere on Earth in the natural world. I think it's depending on the mood that you're in when you see it, it can be very uplifting. It can be very moving. It can just be visually astonishingly beautiful if you're the kind of person that enjoys aesthetic beauty. It can be sort of isolating and make you feel small, but at the same time, I think aurora chasing is such a great social activity. And there's something to be said about the auroras as well. They have such a unique character among all the things that we can look for in the sky. Because if you go and say, look for an eclipse, eclipses are absolutely spectacular to witness, but we can predict everything about them down to a fraction of a second. And for some eclipse chasers, that's part of the fun. If you go and look at a nebula or another galaxy, you're seeing something that changes on the scale that defies the human span. So, your ancestors saw it pretty much the same way you see it. Your descendants will see it pretty much the same way you see it. But when you see the aurora, every single time it's unique. So it has this kind of unique promise to it where you don't know whether the display that you've seen is the best one that you will see. There's always this possibility that the next one is going to be better because it will be completely unique. All that you know is that you don't want to miss that. And so among all of the sky's phenomena, I think it's the most kind of spellbinding, the most mysterious, the most enticing, the most seductive, truly amazing. And actually, if you do get a chance to see it, then I would prefer that you tell me your answer to that question, because I would like to hear that and gather those different perspectives.
Do you remember when you first saw it? Do you remember your sort of earliest memories of seeing the aurora for the first time?
I do. In the early 90s, I lived in Scotland for a few years. I was just a small boy at the time, but I remember vividly seeing the lights over the sea from the beach on the north coast of Scotland and looking up and seeing those lights. And I remember asking my dad was a pilot. So he was working in the Royal Air Force and he would occasionally take those fighter jets up over the North Sea. And he would tell me about the sightings that pilots would get over the sea. And of course, those aircraft have the panoramic cockpit. So you have this pretty much uninterrupted view of the sky and you can travel up towards the Arctic, towards the aurora zone. I didn't get a chance to see it like that at that age, but it was like real mythology to me to hear stories like that. So I was really obsessed and taken by the fact that things like that actually exist in the world. So while I have those memories of seeing it, it wasn't until much later, really, around 2010, when I had my first chance to actually really get a good view of it. I had seen it a couple of times before then. I think of myself as now as being sort of addicted to going and finding auroras for about 16 years or so. So sort of around 2008 was when I had my first proper sighting. But in 2010, I remember really being immersed in overhead displays of the auroras from the Arctic. So that's really the memory that kind of set me on the track that I'm on now.
Yeah, and as you said, each time you see it, it's different. And even when you see images of it, there are all sorts of different shapes and colors and formations. It might be worth delving a little bit into the science behind that. I suppose, first of all, if you can give us a sort of rundown of what actually causes the aurora, and then what causes those different colors and shapes that we see.
Yeah, so starting with that first question, it's good to think, in my opinion, of the aurora as a visible expression of something that we otherwise wouldn't be able to see. And that thing is the so-called space weather environment. So we're all quite familiar with the concept of weather. Here, speaking to you in the summer, we're enjoying some remarkably good weather here in London, at least. But weather can be mild and it can be very adverse. And the same is true of what solar physicists and space weather scientists call the space weather environment, which is really a kind of invisible environment around the Earth, which is flooded with particles that travel away from the sun, particles that we collectively call the solar wind. So this solar wind is traveling from the sun out into the solar system at all times, and the Earth is actually sifting particles out of the solar wind, and some small fraction of the solar wind becomes captured inside another invisible structure, the Earth's magnetic field. And it is the magnetic field of the Earth that gives these particles a tremendous amount of energy and then actually funnels them down into the North Pole and up. I'm using a very kind of Northern Hemisphere chauvinic convention here, but down into the North Pole, up into the South Pole, in two rings which surround not actually the North and South Pole, but the North and South geomagnetic poles, slightly different than the geographic poles. As that happens, those particles are given a huge amount of energy. These are just electrons for the most part. They're funneled down into the atmosphere and they form what we consider to be an electric current. And if you put any electric current through a gas, the electric current has enough energy, the gas can become excited. What happens is the atoms inside the gas, they actually store some energy in their electrons, and then the electrons will eventually give the energy back through one process or another. And as they give the energy back, it's emitted as light. So this excitation and emission process is what makes things like neon lights work, or fluorescent lamps, or even a plasma ball, if you can bring that to mind. And so here we have an electric current that's formed as a combination of particles from the sun and the magnetic energy of the Earth's magnetic field. And we have a gas, our atmosphere. And so this current goes through our atmosphere, it excites a part of the atmosphere, and then those gas atoms actually glow, they give back light, so the sky itself becomes luminous at night. So we're really experiencing the touch of the sun, something that we see during the day generally, but we're experiencing the touch of the sun at night. So it's a kind of sunlight in a way. It's just not being emitted as light from the sun, and we get to experience that at night. So we get these different colors and we get these different shapes. And when it comes to the shapes and the formations, there are various terms. I generally will think of them in two different ways. You have what you might call diffuse auroras. So these are auroras that don't have a particularly well-defined shape, and by their nature, because they're sort of more sparsely distributed over the volume of the atmosphere, they are usually fainter. And then the other kind of auroras, the ones that we get really excited about, I tend to call those discrete auroras. And that's where you get a real focusing of that electrical energy. And that focusing occurs where you get a lot of magnetic flux also being focused. So the Earth's magnetic field is not sort of perfectly uniform like the magnet generated by a bar magnet that you've seen at school, but rather it's quite messy. And that's because the Earth's magnetic field, for one thing, it's being buffeted by the solar wind at all times, and that's causing it to deform and change shape and respond to the magnetic components of the solar wind. It's also being generated by a kind of a fluid magnetic dynamo beneath the surface of the Earth. And so the Earth's magnetic field actually moves in ribbons and has these kind of sheet-like structures that oscillate, and sometimes they split apart and sometimes they form back together. So as those structures move around, you get this increase and decrease in the magnetic flux. So you get an increase and decrease in the focusing, kind of the lensing of that precipitation of electrons coming down. And when there's enough energy there, the auroras can become very bright. And generally, when they become very bright, you also have quite a lot of magnetic stress. So the auroras will also tend to dance and move in various ways. They might flutter in the sky and create a sort of barcode effect, or they might create these rolling ribbons that move very quickly. We've probably all seen time lapses of the Northern Lights where you take a series of photographs and then you can speed it up, and they don't give a particularly good impression of what auroras look like in real time. It's only recently that we have the technology to kind of film the aurora in real time with very sensitive cameras. But what I've always found striking is that time lapses can show auroras moving rapidly across the sky, but there are occasions when the real-time aurora, the real speed of the aurora, is actually faster than a time lapse. It's so energetic. And so it kind of speaks to the previous question a little bit about this unique character that the aurora has, that it sort of has a personality. It can be very turbulent or it can be very docile. And there are different names for the different kind of structures that form there. I'll also speak very briefly about the colors, because we experience different colors in the auroras just as we experience these different forms. And those colors are all related to the gases in our atmosphere. Predominantly, the two gases are oxygen and nitrogen. Nitrogen is the most common of all. Down here at the surface of the Earth, in what we call the thermosphere, the bit that we actually live in, we have mostly molecular oxygen and molecular nitrogen. But once you get high above the Earth's surface, up to about 250 kilometers or so, the oxygen is predominantly atomic in nature. So it's not the oxygen molecules that we breathe, but it's simple oxygen atoms that are free flying around. There is also some molecular and atomic nitrogen up there as well. And at a very highest altitude that the visible auroras form, we see a red color, and this is predominantly from oxygen. Once you get down to about the range between around about 100 to 250 kilometers, there's a green, bright green band. This is also related to oxygen, and it's also atomic oxygen. So how is that possible? Well, there are different ways that these atoms can give up the energy that they're holding on to. They want to radiate the energy away as light. But in order to do that, the electrons that are storing the energy, if you like, in the atoms, they have to give it back by making something we call a state transition. And these state transitions can vary in how much energy is released in essentially the gap or the height of the state transition. So when you're very high up in the atmosphere, these atoms can travel for several kilometers without interacting with one another because the atmosphere is practically a vacuum at that altitude. And so what happens is these oxygen atoms will travel several kilometers. They don't interact with another atom. They're so lazy. They want to give back the energy. And so the electrons will make a series of small state transitions and give away these low energy red photons, creating this red light. We get a little bit of blue light as well, comes from nitrogen, and they sort of combine together. And that's why we often see a kind of purple magenta hue up there. Then as you come down into the green band, now you have a higher density. I mean, it's still practically a vacuum as far as you and I are concerned. But because the oxygen atoms only travel for a few centimeters or so before they interact with another one, those collisions actually motivate larger state transitions. And so the green, higher energy photons are more likely to be emitted there. And we also get secondary electrons. We get nitrogen that becomes ionized as well by the solar wind that's pouring down. Those nitrogen atoms can have an electron bumped free, and that free electron can go and excite another oxygen atom nearby. And so you get this sort of doubling effect. And as a result, you get a very bright green band. So for the most part, we're used to seeing bright green in auroras. If you actually see the scarlet red that's higher up in the sky, that's quite exotic to see with just your eyes. And when the auroras get very bright and the current is coming all the way down to the lowest point in the auroral band, that's beneath 100 kilometers above our heads, that's where you tend to see bright pink band at the bottom. And that's as a result of red and blue light being emitted by molecular nitrogen down at that lowest altitude that the auroras form.
It's incredible thinking about that we know all that science now, and how just for so long the aurora was just, I must have had sort of like godlike mythological status to earlier communities and civilizations. But I suppose part of that science is the ability to predict the aurora. And that was one of the things I wanted to touch upon, because we're sort of talking about how to observe them. You were saying about how precise we can predict an eclipse, but we can sort of, there are numerous outlets and apps and websites that will enable ordinary people like you and me to work out whether or not an aurora display is going to be occurring at our location at a certain time, aren't there?
Yeah, when I talked about space weather, I mentioned that space weather can be very adverse. And adverse space weather can pose a risk, particularly to our very technologically enabled global community, because it can impact our satellites, it can impact our electrical systems. It can actually put us at great risk. And there have been historic storms that have occurred, for example, in 1859, very powerful storm, that were something like that to happen today, that we might actually see quite a lot of damage and quite high expenses as a result of that, because we have become now, I suppose, more susceptible to adverse space weather. It's become more of a factor in how it affects our lives. But the sort of benefit of being able to predict space weather is that the offshoot is that for aurora chasers like us, we can go out and use that predictive power to discover when auroras will be visible, because auroras are sort of icing on the cake of space weather, I suppose, where most of it might be a bit of a problem for us. The auroras are the silver lining, I suppose that's a better phrase, because it's the nice side of bad space weather. So yes, as a result of the need to understand space weather, we have up to the minute predictive capabilities now about the visibility of auroras. But there is quite a lot of misinformation out there about how auroras are predicted. It's not uncommon, for example, to see charts telling you what the so-called planetary K index is going to be, the KP number, as it's often known. But KP forecasting is still quite a lot of guesswork and using previous data to try and sort of estimate what it's going to be. And the KP number doesn't give you a particularly precise indication of whether auroras will be visible. But what the KP number can tell you is how large the auroral oval is likely to be. So that will tell you if the auroras are likely to become visible farther south. And that's particularly important for us in the UK because we're outside of the regular visibility of auroras here. But also I think it's important to just recognize that the KP number also charts into a scale that we call the geomagnetic storm number, or G number. So if you have a KP number that is greater than 4, then you are in geomagnetic storm territory. And a KP of 5, 6, 7, 8, or 9 corresponds to a geomagnetic storm of a G1, 2, 3, 4, or 5, with a G5 being a very, very severe form of geomagnetic storm. It's possible that you can go off the scale, and it has happened, but typically speaking, those higher KP numbers indicate that the geomagnetic stability is going to be upset. And when the geomagnetic stability is upset, the likelihood of bright visible auroras occurring is higher. So when we look at discrete auroras, when we look at those bands and arcs that dance in the sky, those are generally formed by another kind of geomagnetic event called substorms. And substorms can occur at any time. They can be predicted with a very short range, basically by monitoring a current that encircles the Earth that we call the ring current. And so it's possible to predict, up to about an hour in advance, the likelihood that a substorm is going to occur. And that's pretty useful because it gives us an indication of whether or not we're going to see bright visible auroras. Then if we combine those two numbers, or we combine those two predictive capabilities, we can look to a certain extent a few days ahead, a few days in advance, and see how good the space weather is likely to be for us. Bad space weather, good for us. But then when we're actually out there at night, the odds of seeing bright auroras where we are, it's going to depend sensitively on substorm development. And there are a number of factors that go into that. And we can talk about that if you like. But ultimately, they come down to the necessity of essentially predicting what the space weather environment is going to look like. And we use a combination of magnetic observatories here on the Earth. We actually have spacecraft in space that provide an early warning as well, because they lead the Earth around the sun in its orbit. And as they do so, they're able to kind of get a taste of what the solar wind is like 40 minutes to an hour before it arrives here on Earth. And that gives us an indication of how likely it is that those substorms will develop, how much crackling activity there's going to be, and whether it's actually worth your while to go out and persevere in the cold, because it probably will be cold, to get the best view that you can.
Let's talk a little bit about location then as well, because you mentioned there, I suppose, the rarity of seeing the aurora or the northern lights in the UK. Do you think that if someone really wants to go on an amazing aurora trips for the first time, that Scandinavia is the place to go? Or do you think that you can put a punt on sort of northern Scotland?
Never say never. I was in Florida in May of this year, just a few degrees above the tropics. I would never have expected in my life to see the northern lights in Florida, but I did, because as the news reported at the time, as I'm sure listeners will probably be aware, there was a historic geomagnetic storm in May that brought auroras credibly visible to practically the equator, well into the tropics. And that was a wonderful event to see trending around the world. But I will say that what I saw myself in Florida, you might call the tail of the animal, a glimpse of something slinking behind a rock, the tail of the snow leopard. But of course, you really want to see the real thing. Now, I think Scotland is a fantastic place to be an aurora chaser, actually, because Scotland is frequently, and particularly in the north, is frequently visited by the Northern Lights. And of course, it's woven into folklore in Scotland as well, and in Orkney, for example. So I think it's a brilliant place to be. And I think it's a testament to the quality of the British sky that we can go all the way up to the north of Scotland and experience the Northern Lights. And you can come all the way to the south of England and see the center of the Milky Way. And we really do have fantastic access to the skies on our cloudy islands when the clouds clear. That said, while Scotland can be a fantastic place to see the Northern Lights, it comes down to the frequency. So if you are clued in to those geomagnetic storm alerts and you have the ability to quickly react and to go somewhere nice and dark, preferably, if you live in a city or in a town where there's light pollution, ideally you want to get out of there and get to a nice dark spot. And there's so many brilliant dark sites in Scotland to be viewing the sky from as well. If you can go up to the north coast, that's even better. You can look out over sea and over the North Sea. There's no light pollution to contend with, so it's a great place to look north. But it is about the frequency. So I think if you're in Scotland, having that readiness is brilliant. But if you want to make your own luck, then traveling is a big part of that. For me, having seen auroras in North America, in the UK, Scandinavia, my favorite place to go is the north of Scandinavia. I suppose it's something of a spiritual home for the Northern Lights. The visibility of the lights, they're frequently seen in the Arctic, of course, but then when they occur with some dramatic flare, they can come right overhead and just be the most astonishing sight, sky-filling auroras that go from north to south. So much activity that you don't even know where to look. And also extraordinarily bright auroras that are so bright that you can have the full moon in your field of view and you can still nevertheless see the penetrating green color of that auroral band, even with the full moon in your face, which should be spoiling your ability to see those fainter things in the sky. And then another popular place to go, which I have some great memories from, is Iceland. Iceland is a fabulous place to go aurora chasing, particularly if you want to go over land. It's quite easy to drive around the island and you can get to some great dark spots there. I will say Iceland is very cold. So if you enjoy freezing cold wind coming over the smooth landscape straight into your face, then that's a great place to go. But in my opinion, I think the touch of the cold air is actually a big part of the experience. It was quite a strange thing to see auroras in Florida in May, where it's very, very warm and you're outside in shorts, in the middle of the night. But to be out in the cold air, I think it's part of the perseverance and part of the adventure of aurora chasing. So my recommendation is to think about a trip north. But if you are in the UK, having readiness, having those apps and alerts set up for yourself so that you know when to go out and look, absolutely a brilliant thing to be doing. But no matter what you see in the UK, chances are, if you go north, if you've got the bug, chances are you'll be rewarded with an even better sight than anything that you've seen in the UK so far.
And whenever you've sort of chosen your location and you're ready, can you give any advice in terms of observing the aurora other than look up? Is there anything else that you should be thinking about doing?
It's funny because I have a book, The Definitive Guide to Auroras, and part of that book is about aurora chasing. But as you've just sort of hinted, there's actually not that much that you need to do. If you look up, you will probably see it. It's sort of a gift that it's so accessible and so easy. It doesn't require any special equipment or anything like that. But as with the location, a big part of enjoying the aurora, I think, is suitable preparation, recognizing that it probably is going to be cold, potentially very cold where you are, particularly in the Arctic. So being prepared for that so that you don't have a miserable time, that's a good start. And that means that dressing appropriately. And as they say in many Arctic countries, it's not really the number of layers you wear, it's about wearing the right layers. But I'm not averse to occasionally leaning on some toe warmers and hand warmers as well if the right layers just aren't right enough. Sometimes going the extra mile with a little bit of active heat can be quite helpful, particularly as you're probably going to be standing outside for a long time, completely enraptured by the sky, freezing without even realizing it because you're so emotionally overwhelmed by the power of what's happening above your head. So preparing in advance, very important. I think if you're planning an aurora trip as well, there's a lot that you can do to make your own luck. So firstly, traveling when the moon is new, as with many applications in astronomy, traveling when the moon is new is generally better because you get access to darker skies. And so as a result, the fainter auroras are going to show better contrast against that darker sky. Of course, you want to be traveling in the winter months, but if you want to make it a little easier on yourself, you might want to avoid December and January because those are the coldest months, and instead travel between the months, for example, of September to November or February to late March, and that's going to give you a better opportunity. And if you really want to increase your odds, you could consider traveling around the equinoxes as well. There's a well-documented equinoctial effect, meaning sort of associated with the equinoxes, where auroras generally appear with a slightly higher frequency, or in the case of geomagnetic storms, they can actually be much stronger. This is connected to a physical process, and the best hypothesis we have is known as the Russell-McPherron effect, which describes the alignment of the Earth's magnetic field around the equinoxes. It's not primarily aligned towards or away from the sun, and so as a result, there's actually an increase in the efficiency of the transfer of magnetic components from the solar wind into the Earth's magnetic field. So it can increase the amount of material that gets sifted into the Earth's magnetic field, and it can increase the destabilizing factors of geomagnetic storms and make them more enhanced. And the equinoxes also have the benefit of being relatively clement times to travel to the Arctic, because we're talking about late September and late March, so not really the coldest time. For my money, the luckiest month to travel is February, but that's just because I have a logbook with hundreds of sightings, and February always seems to turn up the best views. Probably not valid statistical data, however, more just kind of personal outcomes. So your mileage may vary, but February's, for my money, is quite a good time to go. And I'm very much looking forward to next February, actually. I've got a sort of feeling in my bones about it. Not a very scientific thing to say, but there you go. And then I suppose one last thing I can mention is photography. If you want to take a picture of the Northern Lights, the good news is there's no better time to do it, because you can point pretty much any smartphone made within the last 5 years at the sky, and you will get a picture of the Northern Lights that will astonish you. But if you do plan on taking photos, then just make sure that you're familiar with the gear that you're going to use. Take some time to set your camera up indoors, because when you're out there in the cold and the dark, it actually gets pretty difficult and pretty fiddly to use those things. So either set them up before you go out, or just get used to operating your camera in the cold and the dark before you subject yourself to it, because otherwise you might find that you have quite a frustrating experience. And if you're a first-time aurora chaser, that would be particularly sad. We want to, for sure, for you to get the bug. So we want to make sure that you have a really good first experience. And so being prepared there's a good idea. If you are struggling with your camera, my advice is always the same. There's probably someone around you who's taking a very good picture. So instead of worrying about it, try to take some pictures up here instead, because you can't share the pictures you take up there, but you can feel them, and they're much more sentimental. So just try to enjoy it with your eyes, make some really vivid memories. It's the memories that I think about and not the pictures I take.
Yeah, true for most things in life, really, isn't it? People should reach for a camera rather than enjoying the moment these days. Just wanted to finish on, you mentioned there you were looking forward to February, and it's sort of nice to touch on thinking about that and thinking about the months ahead, because it does feel like now is one of the best times in sort of recent memory to see the aurora. And I guess as we approach the peak of the solar cycle, do you think that this and 2025 are going to be the years of the aurora?
Yeah, and I'm not a solar physicist myself, but I have a few close confidants who are very good when it comes to predicting solar cycles and things like that. They have a good amount of experience. So my understanding is that the cycle that we're approaching the peak of now, it's doing well. It's looking better than the previous cycle, which peaked back in around 2014, I believe. And then we had, of course, around 2002, 2003, a pretty strong peak as well. So there were some great sightings, but it's getting on for 20 years ago. You do have to wait quite a while to make the most of the solar maximum. We're approaching the maximum. It's possible the maximum has arrived. We don't actually know when the solar maximum has arrived. It takes 6 to 7 months to look back to know that you're in the decline going towards the solar minimum. But there have been recent predictions which kind of improve upon previous methods, suggesting that the maximum that we're going into could actually give us several strong seasons of aurora chasing, could have quite a long tail. So as a result, I suspect at a minimum that this season, 24-25, and the next one, 25-26, are going to be fantastic. But perhaps this coming one will be the better of the two. So I strongly recommend, if you're kind of on the fence about going aurora chasing, this is the season, I think, to take the plunge, 24-25. And, if for any reason you can't, then do not fail next time, 25-26, because once we go into the minimum, it's not that you can't go and see the Northern Lights, but it's just that the chance of those extraordinarily beautiful displays, those once-in-a-lifetime displays, they go up during the maximum. It's that frequency of strong geomagnetic storms that greatly surges during the maximum. So we're expecting, any day now to start really being able to see that increase in that frequency and be able to kind of recognize that we're at that peak point, either just past it or still approaching it. So I don't know exactly when that's going to be, but either side of the maximum, there's still that increased frequency. And so this season coming up, starting in September, going through to March, going to be a really good aurora season, I think, for anybody that takes the time to go and experience it.
Amazing. I mean, that's just fantastic insider knowledge, Tom. Thanks very much for coming on the podcast today and sharing that with us. And it's always fun to talk Northern Lights with you. I hope to get to do it again soon.
If you're tuning in, then all I can say is I wish you the very best of luck with your aurora chasing, and please reach out to me and let me know what your experiences are like, because I always love to hear about that.
Thank you for joining us for this episode of our special series all about the aurora. We'll be back with episode 2, The Science of the Aurora.